Okay, I'll introduce myself.
Yep.
My name is Shirley Meng from Nano Engineering. It's my great pleasure to speak on behalf of my engineering colleagues. I see some of them in the audience. An Achilles heel is a deadly weakness in spite of overall strength, and which can potentially lead to a downfall. So my talk today is hope to address three main messages. The first one is what critical role energy storage can play in our sustainable future. The second one is how can we turn this potential threat into opportunities for this campus. And the third one is why do I think UCSD is in the perfect position to tackle this challenge. So this is the energy landscape when I joined UCSD campus. Okay, I know it's a very busy slide. I'll guide you through, but let me show you first that after 4 years of hard work, what happened. Do you notice any differences? Yeah, change is really hard to come. Okay, so let me highlight two major things, okay? The first one is actually both solar and wind has almost tripled. But because their baseline is so low, they started very low. So the overall energy landscape does not change, even though that we have tripled the solar and wind penetration. You see that nuclear is going backwards, which probably is not a good news for the United States. And the natural gas has increased significantly. The main thing I want to draw your eyes on is this transportation section, which is very heavily petroleum fossil fuel based. And the second one is the electricity generation. There are very big difference between these two. The first one is that petroleum, the transportation section is almost dominated by petroleum, but the electricity generation is actually very diverse, the portfolio. You have solar, wind, geo, and natural gas, and coal technology. And what bothers me most when I was a graduate student is you look at the waste coming from these two sectors, okay? In the electricity generation, it's more than 2/3 of energy is wasted. In the transportation, it's even worse. More than 70% of the energy is wasted. So as engineer, we have to find the solutions. Our sustainable future will rely on all these new technologies, including the one Jonathan has mentioned, biofuel. And energy storage plays a role here. Mainly, I'm looking at the big pictures. Let me talk about the big scale picture first. For the grid storage. Before I dig deep into this graph, I want everyone to be on the same page. This is my one chance opportunity to educate my colleagues the difference between power and energy. Okay, so on the x-axis is power. The y-axis is time. Power times time give you energy. Okay, Nate Lewis in Caltech has numerously shown this graph, which does not represent the whole picture of energy problem we have. Okay, you have a light bulb that is 1 watt, that toaster that use 1 kilowatt hour, but you only switch on your toaster for 1 minute, and you switch on your light bulb for 16 hours. The energy used in these two devices are equal, but the power is 3 magnitude order differences. Okay, so when we talk about transistors, we're dealing with nanojoule or picowatt hour. For microelectronics, we deal with joule level, and our brain, like a light bulb, 20 watt. If you think very hard, you consume 20 watt. And for some of us, only work 2 hours a day, so that's the amount of energy you consume. And Tesla is in terms of megajoule kilowatt hour. So I hope everyone is on the same page with me because we have to separate the issue of power and energy. Okay, and now let me talk about the research programs that we have been funded through DOE, NSF, and the Department of Defense, and including several companies in the Bay Area. We all have range anxieties. Okay, this is somewhere I really need help from social scientists. Okay, less than 10% of people drive more than 100 miles per day for commuting to work. but almost 80% of people are unwilling to risk to buy a Nissan Leaf, which is on exactly give 100-mile driving range or 60-mile driving range, 100 kilometers. So as a game changer, in several car companies give the option of plug-in hybrid. And I want to mention battery is an energy storage conversion devices. We don't care where the energy comes from. It can come from fossil fuel. It can come from the wonderful biofuel that UCSD can develop. We convert this energy. We store energy. We provide mobility in the transportation section. And this projection is just a cartoon, okay? Don't take it too serious. But I'm kind of sick and tired of people using the argument that, okay, we're going to run out of oil, so we have to do this. This is not the point, okay? The Minister for Oil in Saudi Arabia, he has a famous saying that the Stone Age did not end because we ran out of stone, okay? We transit to better solution because we're going for better efficiencies. Okay, electric driving is absolutely much more efficient than internal combustion engine. And I know we are all highly intellectual people here. We are obsessed with efficiency. So that's my main point. Okay, so for grid storage, on this picture, it's pretty clear all the battery technology is not on the competing scale with the pumped hydro and the compressed air, but we have a target now in order to beat the electricity price of, for example, the regular grid price. And some people will ask me always, where's the natural gas? Okay, and the natural gas is not on this landscape yet because the picture is made more than 5 years ago. At that time, shale gas was not economically viable. So you can see the breakthrough in the shale gas definitely changed the landscape. But we don't consider natural gas as a threat. Actually, natural gas is a bridging fuel that will buy us who work on renewable energy more time. Okay, natural gas combined cycle turbines are much more high efficiency, so it is a greener technology, but it's not, does not solve the carbon dioxide problem. So I have been very fortunate to work on this topic for 5 years on UCSD campus, solving problems with batteries, make it last longer, make it store more energy, and I have been really fortunate. Up to this year, I have published with physics, chemistry, material science faculties, co-authors, different papers. And I think UCSD has this perfect location, and we have a 45 megawatt microgrid thanks to some of the major contributors from the utility side that we have in Chinese. We call it 天时地利人和. It means the perfect location, good time, and right people. So I think you can read these slides while I'm answering the question. Thank you.
Okay, a couple. All right, while we're waiting, I have one. Where's if electric engines are so much more efficient, where's all the energy loss in electricity then? Is it the heat while you're generating? Why is there?
Oh, no. At the 2012 landscape, the electric cars are not significantly penetrating the market yet. So most of these losses you're seeing in that graph still comes from major petroleum internal combustion engine run.
I know, but you said but even in electricity, most of the energy is lost before it gets onto the grid.
No, actually, electric driving, the efficiency is pretty high.
Really high, okay.
Yeah, more than 90%.
Okay.
Yeah, the only loss is the ohmic heating.
Okay.
Yeah.
Yeah, I'm glad you mentioned battery life because I think that's one of the big issues right now with the electric vehicles that are out there, one of the big concerns with John Q. Public as a potential buyer.
Yeah, so I think no batteries last forever because we are moving ions. And unlike electrons and holes, ions need physical space. So that will generate a lot of the defects, and eventually it will fatigue. Just like the airplane constructions, some airplane will retire after 10 years. It will be the same for battery because the airplane goes high pressure, low pressure, high pressure, low pressure, this kind of mechanical fatigue, and the battery materials will go through the electrochemical fatigue. And the good news is this is the market for battery price already happening, okay? Drastic decrease, just like the solar. So if battery life cannot last very long, our engineering solution is that we make it really cheap to replace.
Okay, so we should keep going. Thank you very much, Shirley.
Third one is, why do I think UCSD is in the perfect position to tackle this challenge? So this is the energy landscape when I joined UCSD campus. Okay, I know it's a very busy slide. I'll guide you through, but let me show you first that after 4 years of hard work, what in spite of overall strengths, and which can potentially lead to a downfall. So my talk today is hope to address 3 main messages. The first one is what critical role energy storage can play in our sustainable future. The second one is how can we turn this potential threat into opportunities for this campus? And this happened. Do you notice any differences? Yeah, change is really hard to come. Okay, so let me highlight 2 major things, okay? The first one is actually both solar and wind has almost tripled, but because their baseline is so low, they started very low. So the overall energy landscape does not change, even though that we have tripled the solar and wind penetration. You see that nuclear is going backwards, which probably is not a good news for the United States. And the natural gas has increased significantly. The main thing I want to draw your eye. Okay, I'll introduce myself. Yep. My name is Shirley Meng from Nano Engineering. It's my great pleasure to speak on behalf of my engineering colleagues. I see some of them in the audience. An Achilles heel is a deadly weakness